Okay, hello everyone. Welcome to the next session of D&F block element. In this session, we will be looking into magnetic properties, coloring of the compound, like why they are colored and how they are colored, what are the colors, and catalytic property of D block elements. And ultimately, we will be looking into the alloy formation. So let's begin with this topic. So you can see magnetic property. So according to the magnetic property, any substance is divided into three main categories, that is diamagnetic substances, paramagnetic substances, and ferromagnetic substances. What are the properties? The diamagnetic substances are weakly repelled by magnetic field. Paramagnetic substances are weakly attracted by magnetic field, and ferromagnetic substances are very strongly attracted by magnetic field. Again, the same thing which has been repeated. We studied the same in physics, as well as we have studied the same in solid state. Now here we see that paramagnetism is arising due to unpaired electrons. So there is a formula that is known as spin only formula, which tells us the magnetic moment mu is equals to root over of n bracket n plus 2. So this is how we calculate our magnetic moment in Bohr magneton. Capital B, capital M are the initials, where n here is the number of unpaired electrons. So just make a note of this. So this is your spin only formula used for calculation of magnetic moment in unit of Bohr magneton. Now if you see, these are our ions, some of the ions. The configuration is something like this: 3d0, 3d1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you see, the number of unpaired electrons will be 0, 1, 2, 3, 4, 5, and from 3d6 the pairing starts. So when the pairing starts, it again goes to 4, 3, 2, 1 and 0. Now, using our spin only formula, that is this one, mu is equals to root over of n into n plus 2. When you use this formula, you can calculate your magnetic moment. So these are your calculated magnetic moments, and these are the actual readings which are observed through experiments. So you see, they are more or less similar, or more or less they are in agreement. Okay. Next, formation of colored ions, very important part. So here, why we see coordination complex to form different colored compounds. So what is happening in all this? We have d electrons, okay, that is inside our d orbital. We have the d electron. So since the most of the d orbital is empty, you can see in all this 9 electrons, 9 spaces are empty, other 8 spaces are empty, and a lot of other orbitals are empty. So what happens actually, the ion may get excited, and the since the energy difference between d orbital is not that much, so there might be a transition between d to d orbital. Okay, so when an electron from a lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light which it has observed. Okay, so it will absorb some light, and the complementary color will be what we will see. Okay, so the color observed corresponds to the complementary color of the light which has been absorbed. Okay, so this is the idea. Okay, now here also it depends. Okay, which are the ligands, okay, what is the ion. Now if you see, in water solution, if you have water H2O as your ligand, so some of the ions are V4 plus, you can see the color, V3 plus, Mn2 plus, Fe3 plus, CO2 plus, Ni2 plus, Cu2 plus. So these are the colors of these ions. Note that in all these, the ligand is water molecule. Okay, so it depends on the nature of ligand also. So what do I mean by ligand? Okay, so let's go into a little bit more detail. So ligand here means this. You can see FeCN6. So Cn, cyanide, is your ligand. Same way, CuNH3 4, the whole is your coordination complex, 2 plus is the charge, NH3 is your ligand. Same way, PtCl4 2 minus. So Cl is your chlorine is your ligand here. Okay, so that is the ligand, and this entire thing is your coordination complex. So because of since we have said that these are the sum of the colors, and why this coloring occurs, that is because of dd electron transition. So again, if you see, here are some of the electronic configuration, and these are the ions and these are the colors. So note that in all these we talk about only the first row, that is the 3D series aquated. Aquated means water is your ligand. Now note that 3D10, so there are no DD transition taking place because there are no DD transition are available, spaces are not available, so hence it's colorless. Same way 3D0, 3D0, there are no electrons in 3D orbital, hence compounds are colorless, or ions are colorless, and all the others are having some or the other color. One of the most common color, I'm sure you know, that is Cu2 plus, which is blue in color. Okay, Mn2 plus is pink in color, Fe2 plus is green, Fe3 plus is yellow. Okay, Cr2 plus is blue, then Mn3 plus violet, Cr3 plus is violet, and these are some of the colors which are very much used in salt analysis. Okay, so please remember these colors and remember the reason. Okay, so in Zn2 plus there are no free electrons which can do dd transition. In this there are no electrons only in d orbital, hence these are colorless. Okay, now formation of complex compound. Now why do they form complex compound? So there are multiple reasons to it. One of the main reason is they have empty d orbitals. Now if they have empty d orbital, a ligand comes, like for example Cn minus is a ligand which comes with a lot of electron, so it gives its electron to Fe3 plus in this particular case. Okay, this we will talk why it is Fe3 plus, why not something else. So here it is Fe3 plus, and it takes some pair of electron from each Cn minus. Okay, and hence they are able to form a coordination complex or a coordination compound. Now one special property of all these coordination compound which is not mentioned here is that when you put this in solution, it does not dissociate. If I tell you example of NaCl, so that dissociates in the form of Na plus and Cl minus, but a coordination complex does not dissociate. Okay, so here also I would like to highlight the fact that Cn is having a charge, Cn minus. NH3 is neutral. Cl minus is again an anion. So usually the ligands are either anions or neutral molecules, which gives electron pair to your complex to metal ion. Okay, so transition elements, they form a large number of complex compound. Why? Reason is comparatively smaller size of metal ion, high ionic charges, that is up to +7 it can go. We saw iron here is +3, iron here is +2, so, and here copper is +2, Pt is +2, so that's like high ionic charges are there. And the other reason is availability of d orbital for bond formation. Okay, that is what I was telling, that all these ligands will give electrons in the empty d orbital of this ions. Okay, next, catalytic property. So we have seen that we use all these transition elements in as a lot of catalyst in different reaction. For example, in Haber's process, iron is used as a catalyst. Okay, in contact process, that's for the preparation of H2SO4 sulfuric acid, we saw that vanadium pentoxide was used as a catalyst. Now why they are used for as a catalyst is because they have the ability to adopt multiple oxidation state and to form complex. So we saw the complex, we saw the multiple oxidation state as well. So what happens, like for example, if I take an example of the first series, the first transition series will use 3d and 4 electrons for bonding. Okay, I hope that you remember how the catalyst is increasing the rate of reaction or changing the course of the reaction by lowering the activation energy. Okay, that is again in chemical kinetics. Just to remind you, this is actually the slide from surface chemistry. So you see that this is the catalyst. These are the reacting molecule. They bind on the catalyst surface, okay, and then they form the bond between A and B, and then they detach from the catalyst, and the catalyst can be reused. So this is the process. So you have diffusion, adsorption, then the chemical reaction takes place between A and B, and then desorption, and finally diffusion of the final product AB. Okay. Last point, also because the transition metal ions can change their oxidation state, okay, they become more effective as a catalyst, multiple oxidation state. So these are the reasons why they have catalytic properties. Next is formation of interstitial compounds. We have seen such type of interstitial compound in solid state. So this is again a repetition. If you remember, interstitial compounds are those where small atoms like hydrogen, carbon, nitrogen, they get trapped inside. Note that there is no sort of bonding, but they are physically trapped inside. So there is no, these are non-stoichiometric. Okay, they don't have a proper ratio. You can see some of the example like Fe3H, VH 0.56, TiH 1.7, etc., etc. Okay, so they are neither ionic nor covalent. They are just physically trapped inside. So you see all these are not corresponding to any normal oxidation state of the metal. Okay, because here it is physically trapped inside. Okay, that is interstitial compounds. Now, the principal physical and chemical characteristics of such compounds are they have high melting points, higher than those of pure metals. They are very hard. Some borides, they approach diamond in hardness. Note that diamond is the hardest substance known to man naturally. Okay. Then they retain metallic conductivity, and they are chemically inert. So these are some of the characteristic properties. Now, lastly, alloy formation. An alloy is a blend of metals prepared by mixing the components. Okay, so alloy can be regarded as a homogeneous solid solution in which atoms of one metal are distributed randomly among the atoms of the other. Okay, so it's a homogeneous solid solution. So that's the definition of alloy. Now, why does it take place, or how does it take place? Before going into that, note that alloys can only be formed when the two metals, okay, are having the radii within 15% of each other. Now if you remember the 3D series, they almost have the similar radii. Okay, plus it's a decreasing radii trend, so they are all able to form alloys with each other. So because of the similar radii and other characteristic, they are readily forming alloys. Okay, and the alloys which are formed, they are hard and having very high melting points. So you can see some of the alloys of like ferrous alloys you can have with chromium, vanadium, tungsten, molybdenum, manganese, blah blah blah. It's not limited only to transition metals. You can have non-transition metals also. Like for example, in brass we have copper and zinc, which are forming the alloy. Bronze, it is made up of copper and tin. Okay, so these are actually very very important for our industry. And that's it. So thank you.